Hi, everyone. Thanks for coming. Today we have Wei-kai here. He's a Cornell PhD student. He's a last year PhD student, right? Today he's going to talk about his work, lower bounds for Oblivious RAM with large cells. Let's welcome him.
Thank you for having me. Today I'm going to talk about my recent result on a lower bound for this cryptographic problem of Oblivious RAM. So it is a work in the lower bound, and mostly in this work I will not talk about cryptographic construction. It's a lower bound, so it's rather lower bound analysis, and it is more related to data structure lower bound techniques. But well, in cryptography, we sometimes face with this lower bound problems. So I hope this talk and this work will introduce more data structure lower bound techniques to the field of cryptography, and people here can learn some from previous data structure lower bound techniques, and maybe use them in cryptographic works later in our own crypto work. This is a joint work with Ilan Komargatsky in Hebrew University of Jerusalem. So let me start with the standard random access machine model, or RAM model. In RAM model, we consider an array of memory cells. Each memory cell has roughly log n bits, and each memory cell, in this talk, we fix the parameter b for the number of bits in each memory cell. This parameter b has to store the address of any other cell in the memory. So it's greater than log n. It can be much greater, but it is at least log n. And in the model, we also have a processor that can read or write a memory cell. And in this talk, I don't really differentiate it read or write. And for historical reason, I just call it a probe, that the processor somehow probes a memory cell. That's just a historical terminology used in the context in the literature. So this is a standard RAM model. And in this computation model, that's RAM model, we can solve various kinds of data structure problem, like the data structure problem we have learned in algorithm textbooks. And probably the simplest data structure is just a plain array. That's an array of n entries. Each entry have w bits. In the array, we want to do just two kinds of logical operation on this data structure. That's either set the value of an array entry or get the ith entry in this array. It's like the data structure array is like just too simple, so algorithm textbook don't really discuss how to implement it. In the RAM model, we can just directly store the whole logical array onto the physical memory cell array, and just like a one-to-one mapping, or we can store many array entries in one memory cell if the memory cell is really large. But here for correctness, we want to, every get operation, we want to get the right correct entry of this array. That's the only requirement for this data structure problem. And this problem actually happens in many places and many scenarios in the memory hierarchy. For example, we can think the memory is actually a cloud server that store a huge amount of data, including all the contents of this array. And this processor is actually our mobile device. So the array may be too large to be stored in mobile device. Or in another scenario, we can think the processor is just a processor with some small amount local cache, not large enough to store the logical array. So this processor has to store things on a physical disk. And in all these scenarios, the processor side has only limited space, not large enough to store this logical array. On the other side, the memory has a huge space and it can store the contents of this array. And in most scenario of our, say, memory hierarchy, uh, we have a physical memory cell size B that's greater than array entry, right? Because typically we have an array entry like 64 bits, but either a disk, what's that called? Disk page size or a chunk of data on cloud server is something like megabytes. It's like maybe a million times greater than array entries. So B is usually greater than the parameter W. And throughout this talk, we consider the relation between three parameters, B, W, and array size N. So on the memory side, the good thing is we have huge space, but the downside is the memory side, it can be corrupted by some adversary. In particular, the processor can encrypt the contents of every memory cell, but the location accessed in this memory array, physical memory array, it's part of the protocol how we use the memory. So there's no way to encrypt the accessed memory location. For example, in the scenario of cloud server, the adversary can monitor the communication between the two sides and see which location is accessed on the physical memory. And this can already leak sensitive data from our secure side, that's the processor side, because these physical locations that we touched in memory cells is depend on sensitive data. So to address this issue, the concept or security or the notion of oblivious RAM is proposed by Goldreich and Ostrovsky. It is saying we consider a logical data structure that's an array, and we want a data structure implementation or an algorithm that implement this logical data structure called array, such that the implementation allows an adversary to observe all the physical probes or physical locations of memory cells. And yet the adversary cannot learn anything about what we do in the logical side, that's get and set operations. Of course, in the context of cryptography, we often consider the adversary can be bounded or just it can be polynomial time or unbounded. And if it's unbounded, we sometimes consider perfect security or just statistical security. But this talk is just for lower bound, and proving a lower bound for perfect security is easier because perfect security makes the construction more difficult, right? The construction more difficult means we are easier to prove the lower bound. In our work, in our paper, we do prove a lower bound for computational setting, but in this talk, it's easiest to think we just want a lower bound for a perfect algorithm that implement ORAM. So by perfect, I mean for every possible logical operations of the same length, the corresponding physical probes yielded when the data structure performing this sequence of logical operations, the physical probes is just identical in distribution. So for every possible, this is sequence 1, sequence 2, all these sequences, they all have the same distribution of physical probes. And in this talk, we just need to consider this kind of algorithms. And we just want to lower bound this kind of algorithm or data structures. And before I talk about the lower bound, I have to first quantify what's the property or metric I want to lower bound. So this is a new terminology to some people called the I/O efficiency, but it's nothing new. It is just asking how many physical probes do I need to answer or perform a sequence of logical operations. So this is actually the standard definition of cost in the data structure textbook. Like in data structure textbook, we ask, say, insertion or querying a binary search tree, how much is the cost? The cost is counted in the number of operations you need to touch the data structure, the binary search tree. And here, there's nothing different. We want to ask if we have a sequence of get and set operations, how many physical probes do we need? And there's a sequence of previous literatures. On the upper bound side, there is a trivial one saying if you want to perform if you want to perform one single get and set a logical operation, then, well, for security, you don't care about cost. You can touch everything in the physical memory, but then the cost will be very high. It's proportional to the array size for just one single get and set. It's crazy high, so that's not very useful. And in other more complicated constructions, we are able to get down the I/O efficiency to logarithmic in the array size. On the lower bound side, we also have some lower bound that is logarithmic in array size n. But in all this lower bound, there is a W over B factor here. Again, W is the entry size, and B is the memory cell size. And in many scenarios, I just said that this B could be a disk page size that's megabytes, where W is sometimes just a 64-bit array entry. So in these cases, this W over B factor is not very useful for lower bound because asymptotically, if we have this B factor greater than log n, this lower bound just becomes almost trivial and doesn't match the upper bound anymore. So in this work and this talk, we ask the question, what if the memory cell size B is much greater than W? Can we improve the upper bound, or it's not possible and we have some way to prove a better lower bound? Of course, because I have already given you our title saying we improve the lower bound, so we know it's not possible, but just stopping here and from previous results, we know many algorithms or data structures that can really make use of larger cell size or whatever terminology you call it, maybe disk page size or something else. But when like a standard example is sorting, when the memory size B is greater, algorithms like sorting or binary search tree can really use the cell size to improve their IO efficiency. So it's really tempting to say maybe there is a way to get better IO efficiency also for this ORAM problem. It's just another data structure problem. But in this work, we said the lower bound is better. So we show that it is almost impossible, and the only room for improvement is just logarithmic in parameter B, unlike previous lower bound results saying with greater B, you can do much better. And that's not the case. We show the room is very small. Specifically, extending previous upper bound results, we can show matching upper bound. That's when B is something like square root in n. The IO efficiency is constant, and our lower bound matches this extreme case. So our lower bound actually matches two extreme cases for the range of parameter of B. We don't know much in between for this parameter B, whether in between we can improve lower bound or upper bound, but at least do we greatly reduce the room between upper bound and the lower bounds. So maybe this is a good point to stop and think a bit if you would like to ask any question. Okay, if no, I have like one or two questions or discussions here. The first thing is that the first thing is about the efficiency metric. So in the efficiency metric here, we focus on the IO efficiency. That's the number of probes we touched the physical memory. There's another metric called the number of bits we communicated between the two sides, the memory and the processor. And the relation between these two metrics is just a factor of b. You multiply b, you get another factor, or divide by b, you get another factor. And a good observation here is that when we are able to control this parameter b, increasing b could possibly increase I/O efficiency, but increasing b doesn't typically improve the number of bits we communicated between the two sides. It is because that increasing b typically makes the algorithm to access, that's read or write, a huge chunk of memory cell. So sometimes that's unwieldy or not very useful, because sometimes the algorithm wants to access the storage, the memory, in a fine granularity. So by this observation, one may ask why these previous upper bound constructions, why do they don't depend on B and W? The answer is these upper bounds implicitly assume that B is greater than W. In all these B greater than W case, the number of probes or the I/O efficiency is just depend on N, not depend on B, because increasing B doesn't help with these constructions. But when B less than W, there's additional cost, and we typically don't assume B less than W, because that's not common in real world scenarios. And in this talk, we also assume B is always greater or equal to W. Okay, so next I will continue with the technical part. That's our lower bound model and our proof techniques. So I want to repeat a bit about the lower bound model, because in lower bound we don't have a we don't have a concrete construction. In upper bound we have concrete construction, so we can look at the construction and say this construction needs some specific assumption or property whenever they use it. In lower bound, we have to limit the only way we can limit the problem size is to look at the computation model. So repeating the model or the problem we want to solve is quite important here. I will also use it later, but this model is quite straightforward. It is followed by Yao named it cell probe model. In this model, the algorithm or the data structure implementation gets as input every time a single get or set operation. That's one operation on our abstract data structure, that's array. And then this algorithm is able to perform crazy and unbounded computation using its local space. We assume this local space is very small. It's like constant number of memory cells in size. But this computation is free of charge. So the algorithm can even solve a exponential time problem using its local space. as long as the computation can be performed on local space, any computation is free of charge. But the local space is very small. Okay, so after this free step, the algorithm of the data structure has to, or if it wants to, it can access some memory cells in the physical memory. Then maybe it's a read of a cell or write a cell. The algorithm can go back and do some free computation until it likes and repeat this physical probe and free computation iteratively until this algorithm arrive at some answer. So the algorithm can answer a query operation that's a get. If that input is a set operation, the algorithm doesn't need to answer anything. So this is the model. We count only the number of probes. We don't count the number of computation. So in this kind of model, because we don't restrict the computation, so this kind of lower bound is unconditional and it fits the standard RAM model algorithms. And this lower bound, because there's no assumption, there are strong results, but often the proof is quite challenging. And in our problem, we additionally have the restriction of security. So we also assume the adversary can see the sequence of physical probes for each operation. The adversary cannot see the operation. The logical operation is not visible to the adversary, but the adversary can see the physical probes. So this is the model of our problem. So let's start with a easier lower bound. That's probably the most intuitive one. So in this easy lower bound, we consider a hard sequence that is just using a sequence of set operations to write a long uniform random string into the abstract array. So this long random string has k times w bits. Every time we use set operation to write w bits into the abstract array. Then we retrieve this long random string back using get operations. Just because the random string is very long, no matter what the algorithm, the data structure does, this algorithm must store this long random string somehow, maybe using some crazy encoding that stores the long random string in the physical memory, just because the processor side doesn't have enough space to store this random string. And similarly, during the get sequence, if the algorithm want to restore this long random string correctly, it has to read something that's maybe a crazy encoding from the physical memory. So this is a intuition for our easy lower bound. Actually, this is a commonly known lower bound. So then this is the number of bits we need to transfer from the processor side to the memory side, and then we need some bits back. We can just divide the number of bits by the size of each probe we can transfer. That's parameter b. Just dividing this, we can know some lower bound that some number of probes is needed during this K sequence of operations. And the amortized IO cost per operation is just W over B. This is just intuition, and to prove this lower bound, we need to use a formal compression argument saying if there is a too good to be true construction that can really use a small number of physical probes to implement or answer this sequence of queries correctly, then we can construct a encoder that is capable of compress a random string. But compressing a random string is impossible by Shannon's theorem. So that's already a contradiction. And if we can construct and show a correct analysis for the encoder, then we can prove it. And in this case, the encoder and the analysis is not too challenging. But later I will modify this argument, and it would be too technical. So in this talk, I'm not going into the compression argument. So just knowing the intuition is enough throughout this talk. And actually, the compression argument or the intuition can prove or argue a just slightly stronger statement, that is, the left side sequence and the right side sequence has to share a large enough set of cells. From the intuition we previously have, the left sequence, that's the set sequence, has to write something or transfer something into the physical memory cells, right? But if the algorithm transfers something into the physical memory, but these cells are not transferred back to the get sequence, then they are not useful. So the number of overlapped cells must be large enough so they can transfer to the memory and then transfer from the memory back to the processor side. So this is just a slightly stronger argument or statement compared to my previous intuition. But the point is this set is shared by the two sides. And this is a key property that will be used next. So until now, we have only used the correctness of data structure problem. That's yes?
Yeah, sorry, I don't quite understand how the intuition transferred to this stronger constraint. Could you please explain it again? Sorry.
Yeah, sure. Good question. So previously, the intuition says the algorithm has to transfer some number of bits to the memory and then the same number of bits back from the memory.
Yeah.
But this number of memory, maybe I can use some pen. So say if the algorithm transfer this set of, transfer the random bits into this set of memory, then later this algorithm reads transfer from the memory back to the processor side using this set of memory, then whatever this non-overlapping memory cells, they cannot transfer anything, right? Because the algorithm just touched it and never touched later in the get queries.
Yeah, right.
So only these overlapping cells can transfer between the sets and the gets. So these sets must be large enough to store this random string.
I
Does
see.
that make sense?
Yeah, that makes sense. Thank you.
Yeah. Maybe this set is using some crazy encoding to encode this random string, but any crazy encoding must be long enough to store the random string of k times w bits. So this set is the overlapping set. I mean the interaction set I drew on the previous slide. And this, I will next use this slightly stronger statement to get a better lower bound, better than only W times B. But here now we already have a lower bound that's proportional to the number of logical operations. Okay, so this is a quite famous technique in proving data structure lower bounds called the information transfer tree developed by Petroscu and the domain. So it considers a logical operation, a sequence of logical operation, and the corresponding physical probe CO'd by each logical operation. Say, for some algorithm implementing the data structure, and we fix some, the algorithm may be randomized, so we fix some random tape for this algorithm. And so the algorithm get a sequence of logic operations that set 1, 2, 3, 4, and get 1, 2, 3, 4 for some random value I omitted here in those sets. And this algorithm chose to touch memory, I mean physical memory cells, number 3, 1, 50, and so on. And for each logical operation, then this information transfer technique build a complete binary tree corresponding to the number of logical operations, and associate each tree leaf with one logical operation sequentially. So we have a 8 logical operation, and that's a complete binary tree with 8 leaves. Then each physical probe is also associated with the corresponding tree leaf. I mean, each physical probe is associated with its corresponding logic operation and associated with the corresponding tree leaf. Then this tree technique performs the following to categorize these physical probes. It looks at every physical probe and see if this physical probe was recently was probed before. Like number 21 was not probed before, but number 1 was probed before, and this technique says then if this probe, I mean this memory cell was probed before, then we assign this probe to their lowest common ancestor. So every physical probe is assigned at most once. These probes are not probed before, so they are not assigned. 21 here was not probed before, but 21 here was probed before, so it is assigned to the lowest common ancestor to this previous 21. And we only consider each probe with its most recently probe, I mean, most recent probe to the same location. So this 21 has a most recent same location probe, and it is assigned to lowest common ancestor with this guy. We do this for all physical probes, and then the number of physical probes assigned on the top of this internal nodes is already a lower bound for the total number of physical probes. Some probes are not assigned, and some are assigned, and each assigned is assigned once to some internal node. So just summing up the assignments to internal node is a lower bound, but maybe it's not good enough, so we need to see. And the nice thing in this information transfer tree is that if we look at this specific logical operation sequence, we can divide this sequence into left side and right side. And our easy lower bound says that the left side and the right side of this logical operation sequence has to touch a large enough set of cells. I mean, the left side and the right side has to intersect at a large enough cells in order to have them transfer the random string from the left side to right side. And by definition, this overlapping cell is exactly the number of physical probes that is assigned to the root node of the tree. Let me repeat again. So every cell, I mean, every physical probe in the right side of this tree, if it is assigned to the root node, then there must be a most recent, a previously probed stem cell on the left side, right? Every probe assigned to a root, there must be stem cell probed on the right in order to have this assignment. And so this assignment is actually the set of intersection cells. So,
so in this probe assignment, we only care about the most recent used probe. So there would be no probe that will be assigned to the lowest common ancestor of at the same position.
No, you mean assigned to? No, we never assign a probe to a leaf node.
I mean, let's say probe 1 is assigned to this lowest common ancestor at the second level. Is it possible that later another probe might also be assigned at the same place with probe 1?
So maybe I should explain this again. So this number 1 is the memory cell number 1 that is touched in this operation, right? And then this same cell is touched again in operation, the first operation.
Yeah.
And so in the concept of this easy lower bound, we say there's some information is transferred from set this operation 1 to operation 4.
Yes, right.
And then this cell number 1 is later touched again in this 7th operation. That's a get operation.
Oh, I see.
So we say there's some information transferred again from here, blah, 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 here.
I see. So it is
So
possible that two probes are assigned to a same node in a tree, like probe 21 and probe 1.
yes.
I see.
So I mean, one internal node in the tree can receive assignment from the whole subtree. I mean, exactly the whole right subtree. Does that make sense?
Yeah, that makes sense.
Yeah.
Thank you.
So here we don't really look at the probes assigned to other node. We just look at the probes assigned to the root. And this number of assignments to the root has to be the same number as the set size overlapped by the left side or right side, because they are by definition the same. Okay, so of course we also do some other assignment that's not assigned to the root node, but we will use it next. Here, focus on the root node. We already have a lower bound on the number of assignment assigned to the root node. Then the key observation in the follow-up work, Larson and Nielsen, that's a key observation, is to use security. So the observation is that this assignment of physical probes doesn't need to know the logical operation. So an adversary know only the physical probes can construct this imaginary complete binary tree. It can just look at the physical probes and construct a complete binary tree on these physical probes and perform the same assignment we did in the previous slide. And then the adversary can say, okay, if I observe one instance of, one sequence of physical probes that has some number of assignment to the root node, then the adversary doesn't really know which logical operation it is, but for any two logical operation, I just said in this talk, we consider they have exactly the same or identical distribution of physical probes. So sequence number 1, sequence number 2, they have the same distribution of physical probes. So in sequence number 1, adversary observe it and calculate it and say this, if this physical probes comes from sequence number 1, the probes must assign a linear number of probes to the root node. Then if this physical probe comes from logical sequence number 2, then by the same easy lower bound, this sequence number 2 can be viewed as left side and the right side here and here as well, right? It's like the two subtree of this right child of the root. So this right child of root also should receive a linear number of probes from this second sequence. And no matter we switch between the first sequence or the second sequence, they have the identical distribution of physical probes. So that means the root and the child of root has to be having a linear number of probes at the same time for the same sequence of for the physical probe. So this is like the the hybrid argument in many cryptographic proofs, right? We switch from one sequence, I mean, one, um, we switch from the real message to some other different real message than to some probably dummy message. It's like the same. We can switch from root to right child or new root to another internal node, and then argue they have to be assigned with a linear number of probes at the same time for the same physical sequence. And that's just because by the security, all these logical sequences have the same distribution of physical probes. So we can literally switch between all these internal nodes and add up all the assigned number of assigned probes in all these internal nodes and get a lower bound of n log n, where the first n is proportional to the number of operations in our logical operation. And the second log n comes from the height of the tree. The tree is binary, so the height of tree is just log n. And this W over B factor comes from our easy lower bound. And this is exactly the result and the proof of Larson and Nielsen. Oops, I don't have much time. So maybe let me quickly go through my slides on our observation and go to the conclusion. Our key observation is here. So in the easy lower bound, we said each logical operation, each logical get has to perform some roughly W over B number of probes. But when B is much greater than W, this factor, I mean, this cost looks just too good to be true. Why? Because in our lower bound model, this data structure, this algorithm has to answer a get query and then, I mean, answer this get query before it knows the next query, right? How can this algorithm answer a query if it doesn't know where the next query is? The only possibility is that in this sequence, the get queries are very predictable, right? This get one, the next query will be get two. So the algorithm can know the future queries and prepare for the future queries. But this is not really the problem is. The problem says every query is independent and you cannot know the next query in advance. So, well, from the view of constructing an algorithm or the view of from the view of constructing an algorithm, every query is just like you need to really read something to answer it. The only way you can answer a query correctly is, I mean, there are two ways. The only way, one way is to you really spend the cost and touch something and get some information from the physical memory. The second way is that you are lucky and you have the answer of the next query already in your local space. But the second lucky event happens rarely if we randomize the next query. And this is exactly our idea. We make the queries randomized. So every query is randomly chosen from the query space. Then every query will take roughly constant number of probes and increase the cost or improve the easy lower bound in the argument and slash out this W over B factor. So this observation is basically saying when the query that is get here is randomized enough, it's unpredictable enough, then every query will need constant number of probes. This sounds quite straightforward, but proving it needs some formal compression argument that I have no time to talk about. So just 3 minutes. Okay, so could just ask the problem of set, and here there's another challenge when we change the hard sequence to random queries. We said that this hard sequence will take a linear number of queries, probes, a linear number of probes that is, well, exactly the same as the number of logical operations, but still this set of cells can be small, still having this W over B factor, just because the algorithm, the implementation can really store this K times W long random string in a small set of physical memory cell, right? So this set can still be small, although we can prove the number of probes is large. But in our tree argument, we need a statement for cells. So this statement for cells is not really good enough. So we further changed our sequence to a shorter sequence that has a smaller number of get or queries compared to the number of sets, just because we want to make the size of the set is roughly the same as the number of queries. So with this change, we can use a variant of tree construction and say we just change or modify the binary complete binary tree into this higher arity tree, and we can still switch between logical operations and sum up the physical probes assigned to all these internal nodes and get a lower bound. Here, the log B factor comes from the increased tree arity, because the tree arity is higher, so the tree is now lower. So we still suffer from some factor depending on B, but it is much smaller compared to previous work. It is just logarithmic compared to previous work is like linear in B. So to conclude, we improve the lower bound, and our lower bound matches the upper bounds in two extreme of the parameter B. There is still some gap in between, but still the room for improvement is just logarithmic, because now we improve the lower bound. And our technique is extensible to other more involved settings, and we have some unconditional separation between different settings of ORAM, and our technique is also potentially extensible to other settings. where there are previous works extending the work of Larson and Nielsen. Now we improve the Larson and Nielsen, so we have potential to improve other works as well. I'm stopping here. Thank you for your attention. If you have any question, I am happy to stay here and answer.
Thank you, Wei-kai.
Thank you.
Thanks.
Yeah, I have one question.
Sure.
What would the lower bound looks like if we're not requiring identical distribution, but like computationally close distribution?
Good question. So the lower bound we have for computational setting is exactly the same here. The argument is more involved, like we need to use some more involved analysis, and one question is simplified here that is probably a good practice problem for a probability course. I'm not sure if people are interested in, but the short answer is we can do this same lower bound for computational setting.
I see. Thank you.
And also relaxing correctness as well.
So if there's no other question, let's thank Wei-kai again.
Thank
That's
you.
really a cool result. Yeah.